Spinning tops, a childhood novelty that we all know and love. They're simple, yet elegant, dancing gracefully on a single point as if to defy gravity itself. A perfect harmony of science, beauty, and art. And if you didn't know any better, you might even say they're magical. While their exact origins are unclear, what is certain is that spinning tops are among the most timeless and universal toys ever made. And perhaps to preserve this impressive legacy, it seems as though the entire world has continued to overlook the one fatal flaw of these nostalgic relics. They stop spinning. Think about it. When was the last time you picked up a spinning top? You probably gave it a little spin and watched it go for maybe a good 30 to 60 seconds before it toppled over, forcing you to restart the process again and again and again. But we live in the future, where we have devices in our pockets that can access practically any piece of information within seconds. So the fact that we still haven't perfected spinning top technology is a societal tragedy of the third degree. I say, it's time we put a new spin on this timeless invention. What if we made a spinning top that could spin for hours? One that could seemingly defy physics. One that could truly feel magical. Now that would be pretty cool. Alright, this project is going to hinge on one question. How do we generate spin in a spinning top? The first thing that comes to mind is one of those perpetual motion machines that have an electromagnet in the platform. But that would be too easy, and it would break my one and only rule for this build. Everything that keeps the spinning top spinning must be contained within the shell of the top. And per this rule, I also can't simply slap on a motor to directly spin the top on the surface, as some electric spinning tops on the market already do. Now, the only place I've actually seen a self-contained infinite spinning top is in my favorite movie of all time, Barbie. One of my favorite movies of all time, Inception. Shout out my boy Chris Nolan. So maybe dream sharing technology is the way to go. The only minor issue here is that Elon hasn't quite invented that yet. So I think the next best thing is going to be reaction wheels. Ever wonder how satellites are able to reorient themselves in the vacuum of space? Well, that's due to reaction wheels, which are devices used to rotate or stabilize the system. And while that might sound fancy, you can pretty much boil down a reaction wheel to two main ingredients, a motor and a weighted wheel. If we accelerate the motor and therefore apply a torque to the wheel, my good friend Isaac Newton tells us that our wheel must then also apply an equal and opposite torque back onto our motor, which causes the base of the motor to accelerate in the opposite direction. This phenomenon is otherwise known as the conservation of angular momentum, and with a little bit of physics, as well as a rotation sensor called an IMU, you can even calculate and verify the exact rate that the base accelerates at. So, to make our infinite spinning top, I think we basically just need to shrink our reaction wheel down to a tiny core that we can stick inside of a spinning top shell. Okay then, let's open up Onshape and get to work. Onshape is easily the best CAD software on the market today, and it just so happens that they're also sponsoring this video. Because Onshape is browser and cloud-based, you can access your designs from anywhere without any risk of losing them. More than that, Onshape is collaborative. Multiple people can access the same design, and even branch off of a design to make their own unique version of it. Onshape is both intuitive and adaptable, making it easy to pick up if you're a beginner or get used to if you're more experienced with another CAD software. So if you're looking to start or improve your CAD workflow, then I would highly recommend using Onshape. You can sign up for Onshape's Discovery program today, where you can get 6 free months of Onshape Professional. Link in the description. For a tiny reaction wheel, we're going to need to scale down our hardware. First up, we have this tiny brushless motor used for really small drones. To control the motor, we have this similarly sized ESC, or electric speed controller. I even messed around with the ESC's firmware to optimize some of its power settings. We'll use this Xiao NRF 52840 microcontroller to send commands to the ESC. And to power everything, we have this 3.7 volt battery, which can luckily be recharged anytime we plug in the Xiao. Alright, let's go build it. Sometimes it really does take prototyping an idea to realize just how much it sucks. And that's exactly what's happened here. Remember how I said that a reaction wheel generates spin in the base when the motor accelerates? Well, motors can only accelerate for so long before they reach their top speed. So eventually, the base also stops accelerating. This is known as saturation, and in order to desaturate a reaction wheel, you have to decelerate the motor. But in doing so, you essentially undo your previously generated spin. Now, knowing this going in, my initial plan was to mount the motor on a one-way bearing so that it could periodically desaturate without undoing that spin. But this is a very choppy method. It's kind of like hammering a screw into a block of wood. It's possible, I guess, just unnecessarily inefficient. What you really need is the proper tool: a wrench, a drill. So what's the drill in this scenario? What can continuously generate spin in a spinning top? Well, I've been scratching my head for a while now trying to figure that out. And it wasn't until what felt like my 100th rewatch of Inception that it finally dawned on me. I'm imagining it'll kind of be like swishing a ball in a bowl. If the ball is the tip of the spinning top and the bowl is the surface that it's spun on, then adding vibrations through off-center or eccentric motion creates circular motion in the tip. But what does this look like in practice? Well, normally you'd want a reaction wheel to be balanced, because the second it becomes unbalanced, chaos ensues. But in the case of our spinning top, these chaotic vibrations should actually lead to clean and pristine circular motion. In theory. But theory can only take you so far. So to confirm this theory, I'm taking the reaction wheel and converting it to an eccentric rotating mass, or ERM. This has the exact same electronics hardware, but with an off-center weight instead of a balanced wheel. Fun fact, ERMs are everywhere in your day-to-day life. In fact, I'm quite confident you've experienced at least one today. ERMs are what generate the vibrations in your electric toothbrush, the buzzing in your phone, the haptic feedback in your game controller, and the vibrations in other things as well. Now, we just need to place this core in a spinning top shell, and we should be on our way. Alright, I just have it going at a constant speed. Let's see. That definitely looks like it's spinning electrically. It's not tipping over, that's good. Oh wow. Yes, it's recovering when I hit it a little bit. Sweet! Now that we have the basic concept down, there are a couple of things we need to fix. So, let's go back to the drawing board. The first is unnecessary vibrations. While the off-center weight is supposed to be unbalanced, the rest of the core isn't. To fix this, I added holes for screws to the cover of the core. That way, I can use them as counterweights to balance out all the heavy spots. And with just 2 screws, the difference in performance is astonishing. Next up is the tip. Since the entire shell of the top was 3D printed, the tip wore out pretty fast. So now, I'm going to use a steel ball bearing for the tip, since a harder tip should lead to better performance. That's what she said. Now, with those 2 modifications alone, you can get a pretty decent electric spinning top. But I still think there's more interesting design aspects to investigate here. Which brings me to a question that I've been asking myself since the beginning of this project. What does the ideal spinning top even look like? Should the top be tall or short? Should it be thin or wide? Should the tip be big or small? That's what she said. And should everything be heavy or light? So far, I've kind of just shot in the dark with these parameters, but now I think it's time to fully enact the scientific method to get some definitive answers. Over the course of several weeks, I designed, built, and tested a sum total of 42 different spinning tops. Some would spin for well over an hour, and some would fall after a couple of seconds. In the end, I was able to identify 3 key factors that go into making the ideal spinning top. The first is moment of inertia, which is a measure of an object's resistance to its change in rotation. You generally want a spinning top to have a high moment of inertia, meaning you want it to have a large radius and high mass. This way, you maximize your top's starting energy, Now, when it comes to an electric spinning top, the top's moment of inertia isn't as important, but the moment of inertia of the off-center weight is. You generally want this to be high as well, and this aluminum off-center weight does exactly that. It was machined by PCBWay, and they machined a bunch of other cool stuff for this project, but more on that later. The second key design factor is the height of the top's center of mass. You generally want a top with a low center of mass, so that gravity can't apply as much torque on the top to knock it off balance. The last key design parameter is the size of the tip. Generally, a smaller tip has better performance. That's what you wish she said. But for an electric spinning top, my testing has shown that a medium-sized tip is much better, as it allows for more stability. Steel ball bearings work great as tips, but to really elevate your top game, you can use grade 5 silicone nitride ceramic ball bearings. These provide a much smoother and harder tip to optimize performance, while also providing a nice finish. That is indubitably what she said. Now, outside of the three main design factors, another thing I want to determine is the best control scheme to optimize the top's power flow. I decided to start off by implementing a PID controller into the top's code. This will take in the measured speed of the top, compare it to a target speed, and then determine if the motor needs to spin faster or slower to achieve that target speed. The big hurdle here was figuring out how to get the top to measure its own speed. The Zhao does have an onboard IMU that can measure angular velocity, but its range is too low. Luckily, the IMU can also measure angular acceleration, so using a bit of circular motion physics, I was able to approximate the angular velocity of the top given its centripetal acceleration. Another speed measuring method I tried was building a Hall effect tachometer. Hall effect sensors detect magnetic fields, so by putting a magnet in our off-center weight, we can determine how long it takes the weight to spin each revolution, which allows us to calculate speed. Now, in practice, both of these methods actually sucked, and I found that just spinning the motor at a constant speed worked perfectly fine. So this is your reminder that sometimes you don't need to over-engineer a solution to a non-existent problem. And trust me, the irony isn't lost on me there. Now that we have the science down, I think it's time we focus on the beauty and art aspects of spinning tops. Which brings me to the second sponsor of today's video, PCBWay. PCBWay is an online service for all of your machining needs, from CNC machining to 3D printing to sheet metal fabrication, injection molding, and of course, PCB making. I got these aluminum spinning top shells CNC machined from PCBWay, and they came out looking beautiful. They have that exact designer look and feel that I'm going for. I also got these slightly concave spin plates machined from polycarbonate, which will give the top a smooth and controlled surface to spin on. Don't let your access to machinery limit what you can make. Head on over to PCBWay today by going to the link in the description so that you can turn your ideas into reality. With the Holy Trinity complete, we have our metal and 3D printed spinning tops. So, I say it's time we put them to the test. So in the end, I can get a little over 2 hours of spin time from the tops before the battery dies. And honestly, out of everything I've built, this has to be the most practical in my day-to-day life. I can see myself using this all the time as a cool little desk toy. Now, if you enjoyed this video and want to support the channel, you can subscribe to my Patreon account, where you can receive cool perks like project updates, director's commentaries on every video, and select project files, like the spinning top project files, which come with all the CAD, code, and a step-by-step build guide so that you can make your own spinning top. Alternatively, if you don't want the commitment of a subscription, you can purchase the spinning top project files from my Patreon shop, and I'll link both of those options in the description. So, spinning tops, a childhood novelty that we all know and love. They're simple, yet elegant, dancing gracefully on a single point as if to defy gravity itself. A perfect harmony of science, beauty, and art. And if you didn't know any better, you might even say they're magical. While their exact origins are unknown, what is certain is that spinning tops are among the most timeless and universal toys ever made. And now, I can say I've added a small part to that impressive legacy. And I think that's pretty cool.